Welcome back, Science 10. Mr. Thompson here again. We're doing 1.3 on acceleration. So, by definition, acceleration is the rate of change in the velocity. It's a vector, and so it can be positive or negative. So, if the velocity is increasing, like in the eastern direction, that's to the right, then the acceleration is positive. If it's decreasing to the right or east, then the acceleration will be negative. So some case studies for you to take a look at, right? They get you to go through that in the module book, but let's make sure we made this clear. So positive acceleration. So if an object's moving east and it's speeding up, then the acceleration is going in this direction, and it is, right, increasing in its velocity. If an object is traveling west, so it's going in the left direction or west, the velocity is decreasing, and so it's slowing down. That means the acceleration would be in this direction. Okay? For negative acceleration, if the object is traveling east and the velocity is decreasing, so it's slowing down, the acceleration would be opposite to that, yeah, opposite to the change in velocity. And in the case of the object traveling west and the velocity is increasing, so it's speeding up, so the acceleration would be in that direction. Okay, do you notice something? When the case of it speeding up, where the object's motion and the acceleration are in the same direction, in this case both to the right, then the object's speeding up. Do you notice here, right? In this case here, on the bottom, the acceleration and the change in velocity are both in the same direction and it's speeding up. So in the case of the acceleration and the change in velocity being the same direction, it's always speeding up. When they're opposite directions, then it's slowing down. Okay? All right, let's take a look at acceleration as a formula. So we define it as the change in velocity over change in time. Now on your data sheet, you're going to notice that they have A with an arrow over top. It's a small little arrow there. And that's going to be Vf minus Vi, and they just put that over t, okay, for simplicity, since the time interval is same as change in time, really. Now you have to know how to rearrange this equation to get the different forms of it. So if I'm looking for the final velocity, that's going to be the initial velocity plus the acceleration times the time interval. Okay? And if I'm looking for the time interval, then I'm going to have the following. I'm going to have the Vf minus Vi all over A. So if I'm looking for a specific way to calculate, or a specific variable to calculate in this, then I'm going to make sure I choose these appropriate equations, okay, in addition to the one that's provided. It's very uncommon that you'll be asked to solve for the initial velocity, but that's possible as well. And so the initial velocity would be Vi equals Vf minus A times t. Okay? So that's one possible version here as well. All right, here's some examples for you. So Barton's bicycle accelerates from 6 meters per second to 14 meters per second in a time of 12 seconds. What is his acceleration? We write down the formula. We substitute in what we have. It's going from 6 to 14, so the final is 14, the initial is 6, and the time interval is 12 seconds. And now the calculation. 14 subtract 6, calculate that, then divide by 12. I get 0.6 repeat. Now, in the case of rounding it to significant digits, you have 2, 3, and 3. So in the calculation here, we want to make sure we're going with, here would be 8.0, so 2 significant digits, 0.67. Now the units are meters per second squared, okay? Because it's a meter per second for the velocity, change in velocity, and then we're dividing by seconds here for a unit. Take a look at number 2. If Milhouse has an initial velocity of 20 meters per second and then accelerates at negative 2.4 meters per second squared for 5 seconds, so acceleration is against the motion, okay? What is Milhouse's final speed? So I'm going to use this version of the equation up here, and I'll write that one down. Vf equals Vi plus A times t. I start with 20. Then I add the acceleration, which is negative 2.4, and then I multiply that by the time, which is 5 seconds. And the calculation. Okay, I get 8. Now we'll look for sig digs here. We've got 2 sig digs, 3 and 3. We're going to go with 2, so 8.0 meters per second. Okay, I've done a couple of example problems to get you going. Let's look at number 3. The car has an initial velocity of 0 meters per second and after 5.6 seconds, an average velocity of 12 meters per second south. Now you have to know something about average velocity. See, the average velocity is really defined as the initial velocity plus the final velocity divided by 2. It's like an average of two numbers, right? And so we can calculate that average velocity sometimes in a calculation. In this case, we've given the 12 here. You know the initial velocity is 0, so what's the final velocity? So in this case, I'll just figure out this problem and figure out VF. So initial velocity is 0, I'll put that in here. I'll put in 12 for VF, so 12 equals 0 plus VF divided by 2. 12 is something plus 0 divided by 2. VF must be 24 meters per second south. Right now I'm trying to just make sure I save myself a little bit of room, so that's why I did that one over there. Okay. What is its acceleration? Well, for acceleration now, I can go ahead and calculate it using the formula. Vf minus Vi over t. And so I'm going to put in Vf as 24, take away 12, divided by 5.6. 24, take away 12, which is 12 over 5.6. 2.1. And in this case, meters per second squared. Okay, what distance did it travel in 5.6 seconds? Okay, so this question maybe is a little challenging for a lot, but when you think about distance, instead of displacement, right, we're just thinking about how far it went since it's all in the same direction anyways. Distance is really speed times time, but what speed are we using? Well, on average, we should just use that speed that we're given in the problem here, or that was provided here, 12 meters per second. So on average, that's how fast we're going for 5.6 seconds. And so we use V average times t. Okay? And so this is going to be 12 meters per second south times 5.6 seconds. Now in this case here, 12 times 5.6 is 67.2. And so we look at the sig digs that we've been using here and we round it to 67 meters. Now let's make sure we're clear. This is supposed to be a south kind of thing. Okay? And maybe I was a little hasty on this one here because this should still be south as well. Okay. Now I've done a few example problems for you. I hope that you're getting the right idea. Please email me if you have any questions about this. Thank you very much.